In this lesson, we're going to talk about resonance and hybridization. And so when we look at the foundations of organic chemistry, there's a lot of different topics that we're going to be talking about. So we've touched upon resonance already. We've also touched upon hybridization, right? And so we're going to build off of hybridization to learn about the factors that affect stability. But right now, we are essentially going to see where resonance and hybridization abut, where they connect, and we're going to do that through a few different problems. The first thing is, let's give you an example. Let's clean that up a bit. There we go. And so we'll call this example 1. I can ask you many different things about this molecule. I can ask you the number of pi bonds. I can ask you the number of sigma bonds. I can ask you the number of p orbitals. I can ask you if there is a resonance structure available. But let's go through and answer these questions. So how many pi bonds do I have? Let's color them so they're easier to see. So this would be 1. This would be 2. Oops. This would be 3. Go back to blue, 4. Oops, let's do red on that one. Right, and so we have essentially 5 pi bonds. If we add them up, everything in color is going to be 5. 1, 2, 3, 4, 5. Right, now let's take a look at the number of sigma bonds. Sigma bonds are basically single bonds or the first bond in a double or triple bond. So this would be a sigma bond, that would be a sigma bond, that's another one, that's another one, there's another one, there's another one, there, and there. So let's count that up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a total of 9 sigma bonds. Now that's just what we can see. We have to look at what's implied. And so here we have an implied hydrogen. So that's going to be another sigma bond. And then here we have an implied hydrogen. That's another here, an implied hydrogen there. There are 3 over here. And so now we count them up. We had 9. This is 10. 11, 12, 13, 14, 15, 16, 17. So there should be 17 sigma bonds in this molecule. Now, how many p orbitals are present in this molecule? Now, this is getting a little bit cluttered, so I'm going to clean it up a little bit. I'm going to remove all of the implied hydrogens. You can stop the video and go back through and count yourself. But essentially, now we look at p orbitals. So it takes a p orbital. So there's a p orbital essentially on every carbon that is participating in a double bond. So this carbon participates in a double bond there. So essentially there's a p orbital here. With that, they're connected. That's what forms, I should have drawn this in red to show that that's what formed that red double bond that we had drawn in there. So let me declutter this. We put a red double bond here, and so I'll put the p orbitals there. So this would make 1, that would make 2, and then we go through here. Let's look at this blue double bond. So this blue double bond right here has a p orbital there and a p orbital there. These 2 would form that blue double bond. Again, let me clean it up a bit. I want to make sure that we can see this pretty easily. So those would be another 2. Now let's take a look at that green double bond. there'd be a p orbital there and a p orbital there. So that's another 2. And then here would be 2 p orbitals for this blue double bond, or should I say the triple bond, and then this other bond that is red would have another 2. Right. And so what you would have is there's 2 and then the blue. So 2, 4, 6, 8, 10. So you should have 10 p orbitals total. Now I made a mess of this. I'm going to erase it again. But hopefully you guys see each carbon that is participating in the double bond is going to have a p orbital attached to it. So now let's see if there's an easier way to kind of figure this out. Let's just go to the carbons themselves. So instead of drawing the p orbitals, here's a red double bond. So that's going to have a p orbital, that's going to have a p orbital. This blue double bond is going to have a p orbital on either side of the carbons that it is comprised of, right? That green is going to have, this green double bond is going to have these 2 carbons. So there's 2, 4, 6 so far. Let's keep going. So we called this blue, and then I believe we called this other one red. So then we're going to have 2 here on either side of that bond, the red one, and then 2 there. Right, so now let's count them. I have 2 in the blue, 2 in the red at the top, 4, so that's 4, 6, 8, 10. So that gives me 10 p orbitals, right? And so we can do this with a similar example. Hopefully it's more streamlined now that you know. Let's do, put oxygen there. Okay. And if we were to ask the same questions, number of pi, number of sigma, number of p orbitals, so there we have, draw the lone pairs in. Now let's ask the number of pi bonds. So this would be a pi bond, and that would be a pi bond. So we have a total of 2 pi bonds. How many sigma? Every single bond or first bond in the double or triple bond is going to be a sigma. So let's go back to the yellow for that. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then now we have to draw the implied hydrogens. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So all these yellow are going to be also sigma bonds. And so we're going to have 19 total sigma bonds. All right, now let's continue on the number of p orbitals. At every double bond or triple bond, the end of it is going to have a carbon that has a p orbital or an oxygen that has a p orbital. So this one has 2 atoms that have a p orbital. So that's 2 so far. And then this one has 2 atoms that have a p orbital. So there's a total of 4 p orbitals in this molecule. Now let's go through, and if I can erase some of the stuff around it and write the hybridization of certain atoms. And to save us time, I'm just going to point to those atoms. So this oxygen, both oxygens, I'm going to ask you for the hybridization of that carbon, and the hybridization, I'll choose this carbon right here. And so we'll start from the bottom and work our way up. This carbon has how many groups around it? 1, 2, 3. So it's going to have sp2 hybridization. We were like, oh, you said 3 groups, but then you ended with sp2. Well, that's one. This represents 1 group, and the 2 p's represent 2 groups for a total of 3 electron domains or groups around it. So now let's look at this oxygen. How many electron domains or groups does it have around it? Let's color it green. So it has 1 electron domain, those electrons, that lone pair, and that lone pair. So that's 2. This bond makes 3. That bond makes 4. So it has 4 electron domains. Therefore, it's going to be sp3 hybridized. 1 here plus the 3p for a total of 4 domains. The S represents 1, and the 3 p's represent 3. 3 plus 1 equals 4 domains, right? So we have essentially sp3 hybridization there. Now, let's take a look at this final oxygen. It's got 1 group, 2 group, 3 groups. So whenever something has 3 groups around it, it's going to be sp2. There we go. And so I'm missing this carbon in the middle. How many groups does this carbon have around it? Let's color it red. It has 1 group, 2 group, 3 groups around it, so it's sp2. And so we can also ask the hybridization of atoms, right? And so these would all be valid questions for your test. All of these types of questions are going to be high yield. And so I'll go ahead and circle this in red to notify that it is a high yield concept. Now, let's do another problem and see where the concept of resonance meets the concept of hybridization. When I look at this problem right here, I have a carbon with a negative charge on it. We'll draw in the implied hydrogens here. And so how many electron domains do I have on each of these atoms? So I will call that one, I'll color that one blue. I'll color this middle one green, and then I'll color this final one red. And so these carbons, when we look at the hybridization, remember we're asking you for hybridization of specific atoms, the green, the blue, and the red. And so the blue, let's start. It has 1 domain there, 2 domain there, 3 domain there, and then the lone pair or the negative charge is going to make the 4th domain. So when something has 4 electron domains, it's going to have a hybridization of sp3. 1 domain there, and then 3p orbitals, so a total of 4. So 1s, so 4 domains. This 1 plus that 3 means 4 domains. Right, and so we just leave it sp3. So this is sp3 hybridized, right? Now, let's take a look at the green. How many domains does the green have? 1 here, 1 there, and 1 there for a total of sp2, right? Now this last carbon in the red, how many domains does it have? 1, 2, 3. So it's going to have sp2 character. Do we see that? Okay, hopefully we see that. And now we're going to do its resonance structure. What is its resonance structure? Well, these lone pairs drop down. When the lone pair drops down, there's already 4 bonds to this green carbon, so something has to kick out. And so those electrons kick out onto the carbon. And so now we have its resonance form. Remember, these two exist at the exact same time. So let me draw the hydrogens in there. But resonance does not mean that they're in equilibrium. It means that they exist in the exact same time. And so now let's go through and color these again. So this is where you need to pay attention a bit. There's almost a sleight of hand. Let's take a look at the number of electron domains around this blue carbon. 1, 2, 3. So that's going to have sp2 character. But wait a second. What happened here? It was sp3 here, but now it's sp2. Okay, so the resonance structure changed the hybridization of that atom. The problem is, though, resonance means that they're both those two structural representations at the exact same time. So how can it be sp3 at the exact same time as it is sp2? It can't be. And so what we do is we designate, I got rid of a double bond, we designate, instead of saying it's sp2 or sp3, what we say instead is it's sp2 dash sp3. We can also say sp3 dash sp2, the order does not matter, or we can just go by the lower of the two, which is sp2. So both of these could be called sp2 or sp2 dash sp3. I prefer going with sp2 dash sp3 because it indicates that I know the difference between them. So this is typically how I'll write it to show that their character is both sp2 and sp3. So now let's look at the green carbon on the right structure. Green carbon, 1, 2, 3 electron domains. So what is that? Still sp2. There's that. And then lastly, this red carbon here. What do we have? 1, 2, 3, and there's the fourth domain, so it's sp3. But wait a second, it was sp2 over there. So again, we have to do the same type of thing. It can't be, they can't both exist, the structures can't both exist at the same time if one is sp2 and then it is also sp3. That doesn't make sense. So instead, what we do is we designate it sp2 dash sp3, and then we can say sp3 dash sp2. Saying it's sp3 would be unequivocally wrong in both cases. Number one here, it's 3 groups, so you're never going to write sp3 there. But here, again, you wouldn't say it's sp3. You can't leave it at sp3 alone. You have to say sp2 dash sp3 or it's wrong. Or you can say just sp2, the lower of the two, meaning that there's still a p orbital that is involved in resonance. Right? And so this is how the idea of hybridization and resonance meet. You have to recognize that resonance structures will have a hybrid, essentially the hybridizations of them can be both sp2 and sp3 if you get the resonance. And so this is high yield. This is something that you will for sure be tested on in your exam. And so you got to really get good at this, recognizing, doing the resonance form, and then seeing, okay, in this resonance form, it's sp2, in that one, it's sp3, but it can't be sp2 in one and sp3 in the other if those structures are both the same thing at the same time. So you have to say sp2 dash sp3, right? Remember, a resonance arrow is not equilibrium. Instead, it means it's both at the exact same time. We can't have sp3 in one, so let's say can't have sp3 in one resonance structure and sp2 in another for that same carbon. So the way we solve that is by saying that it's sp2 dash sp3. Or you can equally say it's just sp2. All right, again, this is my preferred method. It shows a deeper insight into understanding how that works, but you wouldn't be wrong.